So yes, in the past year conference I talked about down conversion for solar cells, splitting photons into two. Today my talk will be more geared towards the biomedical field. I will talk about measuring temperature with light. So the first letter there also to me is not an S. It's also not a symbol of hope. For me it's a schematic of a temperature sensor. You can see the red, the hot in the bottom, and then the middle temperature, and the blue in the top, and the scale bars there. So it's a schematic of a temperature sensor, very appropriate for my presentation. So what will I do? I will start with some basics. I will talk about temperature range sensitivity, some important parameters, what makes a good temperature sensor. I will talk about Boltzmann equilibrium, something that can spoil a good temperature sensor. And then we'll talk about temperature accuracy, a topic that is not enough stressed and discussed in our field. Then I will show some application, maybe not all, because I have to hurry up a little bit. But if time permits, I will talk about temperature sensing catalysis, microfluidics, and temperature mapping with high micrometer resolution. And I will end with some conclusions. So let's start. Luminescence thermometry. It uses emission of light by microcrystallites or nanocrystals, where the emission spectrum or the luminescence decay time changes as a function of temperature, and you use that change, you probe that change to deduce a temperature. And there can be different types of changes in the luminescence. The lifetime can change, and then you need a pulsed excitation source and a time-resolved detection, and you typically see that at lower temperature the lifetime is longer, and when you heat it up the lifetime gets faster, and you can use then the lifetime to sense the temperature at the position of your nanoprobe. You can also measure the luminescence spectra. You excite your crystallites, you measure the luminescence spectrum, and then there can be a change in intensity. Typically the intensity decreases when you heat up. You can also have a shift of the peak maximum to different wavelengths. That can be to shorter or longer wavelengths at higher temperatures. Typically it goes to shorter wavelengths. You can look at the width of the peak, but most widely, that's also what I will use today, you look at the luminescence intensity ratio as a function of temperature. You look at two different peaks, and as a function of temperature, the ratio between the two peaks changes, and that is nice because then you do not depend on the alignment or the excitation intensity. It's internally referenced. You just look at that ratio of the two peaks, and that tells you what is the temperature. Just as an example, a very popular system is sodium fluoride doped with ytterbium and erbium. And this is the energy level scheme of just a few of the levels of erbium. It has a 4s3 level, giving nice green emission. About 750 wave numbers above there is 2h11 level. And at room temperature there's some equilibrium between the two levels, and you get emission from the 4s3 level at longer wavelengths here, and also some emission from the thermally populated 2h11 level. And then as you look at the energy difference, it's about 710 wave numbers in this host. And then if you raise the temperature and you scale it to the 4s3 emission, you see that the relative intensity of the 2h11 emission goes up, goes up, goes up. And from the ratio of the two peaks, and the nice thing of lanthanides, they have nice sharp emission lines, so you can very accurately determine the area for the 4s3 emission, the area of the 2h11 emission, and from the ratio of the two, you can deduce the temperature. And if there's Boltzmann equilibrium between the two, meaning that the equilibration between the two levels is much faster than emission from either one of the levels, then it follows Boltzmann's law, and when you plot the natural logarithm of the intensity of the higher energy emission over the lower energy emission versus 1 over t, you get a straight line with the slope of the delta E, the energy difference between the two levels over Boltzmann's constant. So that makes a very nice internally referenced temperature sensor. And then for those of you who are not in the field of lanthanides, this is a very confusing picture. For those of you who work in the field of lanthanides, that's your toolbox, that's what you work with. There's many different lanthanides with a whole scale of energy levels, with different energy differences, different regions where they can emit in the UV, the visible, the infrared, all those energy levels arising from interactions between the electrons in the partially filled fresh shell. We can use all those energy levels to make different types of temperature sensors with different delta E's, different spectral windows. So it's a very active field to design the temperature sensor of your dreams. And this is just an overview of some of the emissions of lanthanides in different spectral regions that are being used for temperature sensing. And there's quite some review articles from pioneers in the fields. Ferenc is here, Arthur Betankiewicz is here, Danny Jacques. Where is he? Luis Carlos. So if you're interested, many reviews have appeared, giving a very good overview of the possibilities of the field. And also many applications in temperature sensing and also temperature mapping in the biomedical field, where you can probe temperatures in living organisms and also probe temperatures inside cells. So it has a high biomedical relevance. So first topic, temperature range and sensitivity. To characterize how good a temperature sensor is, there's different parameters that are used. One is the absolute sensitivity, that's defined as the change in the intensity ratio per temperature interval, but more popular is the relative sensitivity, which is the change in the ratio per temperature interval divided by that ratio. And of course you want a large change in your parameter when you have a small change in temperature, so then you can reach a high sensitivity and a good temperature sensor. Now in the field, when we entered it about 6 years ago, there was a lot of papers and nice high reported, high relative sensitivity, but a good foundation, a good mathematical background of what is the optimum energy gap for a certain temperature interval that you want to measure in, and also when do you get Boltzmann equilibrium, that was lacking. And Marco Suta entered our group, and here he is at his PhD defense. I was present there, and in Germany they have this strange habit, I guess, to give the candidate a hat that reflects their life until then. So, yeah, very nice from Mark, and also a lot of hair, which he usually lacks. So, one of the things that he did is he calculated what is the optimum temperature window. And of course that's a balance between how much of a change do you get between the emission from those two levels and the intensity of those emissions. And then when you go to, and this is plotted as a function of R, so along the x-axis R, which is the energy gap over kBT. So if you have a high R, it means that you are at a high energy gap compared to the temperature, so yeah, as a specific low temperature, which means that most population is in the lower level. And of course, if you increase the temperature, then the relative change in the population of the higher level is very high, because there's hardly anything in the higher level, and when you increase the temperature, you get a little bit. So the delta N over N total is very high. But the population of the higher level is very low, so you get very little emission from the higher level, which means that you're not very sensitive, you have a very weak signal. And then if you increase the temperature, you see that the delta N over N tot goes down until you reach very high temperature, where you have equal populations of the level 1 and 2 at the highest temperature. But at the same time, if you increase temperature, the population of the higher level goes up. And what Marcus showed very nicely mathematically, that the optimum window is for the temperature range, where R is between 2 and 2 plus the square root of 2, so 3.41. That's the ratio where you have the optimum response for temperature sensing. And he made a nice scheme where you can define, is my thermometer, is the ion and anti-level gap that I want to use good for that temperature window, and you can find that in the paper. So the optimum temperature window is between 0.3 and 0.5 times delta E over Kp, the Boltzmann constant. Second aspect that is important is Boltzmann equilibrium. For this temperature sensor to work, you need Boltzmann equilibrium. Otherwise, this equation doesn't hold. So the equilibration between the two levels, 1 and 2, has to be much faster than emission from either one of the levels. And now we can distinguish different situations. For a very large energy gap, much larger than the effective vibrational energy, because vibrations is what make the level equilibrate. For a very large energy gap, you just get emission from level 2. Level 1, if that's populated from all the way, also gets some emission. But you don't have Boltzmann equilibrium, so when you change the temperature, you don't have Boltzmann's law. When you go to higher temperatures, there may be some phonon-induced relaxation from level 2 to level 1. And when you increase the temperature, actually emission from the lower level will increase, because this is thermally stimulated, this becomes faster. But again, you cannot use that Boltzmann equation to determine the temperature. Only when the temperature is really high and the upwards phonon absorption and the downwards phonon emission, when those processes are both much faster than emission from level 2 or emission from level 1, only then this Boltzmann equilibrium in this nice straight, when you have 1 over t versus the natural logarithm of the ratio, only then it works. And so you need Boltzmann equilibrium for your thermometer to work. And we did some theoretical work where we looked at how does the number of vibrations, the number of phonons in your lattice that you need to bridge that gap affect the onset of Boltzmann equilibrium. And what we found is not very surprising. When you need only one phonon, this onset of Boltzmann equilibrium is at a much lower temperature than when you need 2 or 3 or 4. The reason being, if you need 2 or 3 or 4 phonons to bridge that gap, it's a higher order process. It's a second order, third order, fourth order process. So it's much slower. So you need to go to higher temperatures, higher phonon occupation numbers to realize equilibrium. So that was the theory. Then we also did some experiments to prove, and that's indeed the case. And here we compare 2 types of lattices. We put the europium 3+ ion, my favorite ion, into yttrium oxide and also into lanthanum phosphate and lanthanum borate. In a phosphate and a borate, you have 1200 wave number, 1400 wave number high energy vibrations. So you need only 2 vibrations to bridge that gap between the 5D1 and the 5D0 level. And if we look at the intensity ratio of the 5D1 over the 5D0 emission, you see that in the oxide, initially if you increase the temperature, again 1 over T is along the x-axis, so going from the right to the left we increase the temperature, initially the relative intensity of the 5D1 level goes down. So you go to higher temperatures, but still the emission from the higher level decreases because it gets faster relaxation to the lower level. And then at some point, when this equilibration between the two levels becomes very fast, then you get the Boltzmann equilibrium and you get the straight line when you plot the natural logarithm of the intensity ratio versus 1 over T. But the temperature is 560 Kelvin, very high temperature. When you go to the higher phonon lattices, the phosphate or the borate, then you see it's already around 400 Kelvin. And that's important, and people often ignore that. They assume that they have Boltzmann equilibrium, but in some of the thermometers that are reported in literature, at a lower temperature end, they are not in Boltzmann equilibrium. You see deviations, and then you get the wrong temperature when you use the Boltzmann equation. Then there's more factors that are important. The distance between the lanthanide ion, the vibrations, the ligands plays a role. Whether you have a magnetic dipole or electric dipole transition for the equilibration makes a difference. So if they're coupled by a magnetic dipole or electric dipole transition, you prefer the electric dipole transition because also the transition on the vibrations in electric dipole transition, we saw a clear influence. The erbium ion, that's that favorite ion, has a very strong electric dipole transition between the 2 levels that equilibrate. So there the onset temperature is much lower than, for example, for europium or neodymium, where you have a magnetic dipole transition. So all of those are considerations that you need to consider when you want to optimize the temperature range over which you can use your thermometer. And of course you want to make that as high as possible as well. Also the dopant concentration can play a role. If you look at neodymium, nice ion, it has emission in infrared, and for biological samples that's nice because it's in the transparency window for biological samples, and the 4F3Fs and the 4F5Fs levels are used. The gap is about 1,000 wave numbers, so you see a 880 nanometer emission from the lower level, 810 emission from the higher level, and if you, for the 0.1% neodymium, plot 1 over T versus the ratio, logarithmic scale, you see a nice straight line, you get the energy gap of 1,000 wave numbers, works very well, but of course 0.1% is a very low concentration, absorption is low, so you get a pretty weak signal, so then you think, let's increase the concentration, we go to 1 or 2 or 5% neodymium. Well, then a problem arises, because if you go to those higher concentrations, cross-relaxation sets in, where one neodymium ion can transfer part of its energy to a neighboring ion. For example, this process, 4F5Fs to 4F15Fs, is resonant with the 4I9Fs to 4I15Fs absorption on a neighboring neodymium. And that means that the population decay of those levels becomes much faster. The equilibration by the phonons stays the same. And that means that Boltzmann equilibrium sets in at a much higher temperature. Instead of room temperature, which you had for the 0.1%, it now sets in around 450 Kelvin. So important to realize that. Something to always need to check, what is the temperature range over which my Boltzmann equilibrium applies and where I can use my temperature sensor. Temperature accuracy. If you read the literature, sometimes people have some very large change in ratio of their emission intensity as a function of temperature, and then they get a relative sensitivity SR that is really nice, maybe 5% per Kelvin. And then from that they calculate what accuracy is, and then you see reports where they say the accuracy is 10 millikelvin. Well, there's other factors that determine the accuracy, and the luminescence thermometers at best are 0.1 Kelvin accurate. So that's the pitfall second that I would like to discuss. The focus that's in the literature on the relative sensitivity. There's other factors that need to be considered. One is again that the temperature range, and for all Boltzmann thermometer, the temperature range that you can use with a good relative sensitivity is pretty small. It falls off very rapidly when you go to higher temperatures. The thermometer becomes less sensitive. And the way around it is to use energy transfer thermometer. Another important aspect is it's not only relative sensitivity, but the brightness, the intensity that you get from your probes is very important in determining how accurate you can measure temperature. And then there's also systematic and statistical errors. Error analysis is important. So in our Nano-TB Tech consortium, a nice European vet open grant focused on luminescence thermometry, we had a nice webinar with the title, "In Luminescence Thermometry We Trust." Can we? And that's a very relevant question, and we have to consider that in the field. So, increasing the temperature range. You can use energy transfer thermometry, where you use energy transfer between lanthanide ions to really extend the range much wider than what you can use with the Boltzmann thermometer. And as an example I have here, and that takes some time, but a holmium thermometer. And the nice thing is also the visual. You see at room temperature it emits red. With 12% holmium, at 873 it's green. The reason for temperature dependence is the following. When you look at a low holmium concentration, it always emits in the green. The reason you excite in the blue in the 5S3 Hertz level, then there's a rather small gap to the 5S2. You get multiphonal relaxation, you get a nice green emission. And the relaxation further on to the 5F5 level, that gives red emission. That is very slow, the gap is bigger, you need more phonons, so you get basically green emission over the whole temperature range. But now, when you go to a higher holmium concentration, for example 12%, then from this blue emitting level you cannot only have multiphonal relaxation to the green emitting level, but you can also have cross relaxation with a neighboring holmium ion, where you go from 5F3 to the red emitting level 5F5, and the neighboring ion goes from 5I8 to 5I7. And then you get red emission. So for 12%, this cross-relaxation process wins from the phonal relaxation process from blue to green, so you see dominant red emission. Now, this cross-relaxation is not very temperature dependent, it always has about the same rate. So if you start heating your sample up, then the multiphonal relaxation becomes thermally activated, you get faster relaxation to the green emitting level, and you see the green emission become stronger. And now again, the ratio between the red and the green emission is a function of temperature. We did a very careful analysis to also have a good model for that. Often those ratios between energy transfer, you just measure it and that's your calibration curve. We also wanted to really understand it. So for the low doped host, we measured the luminescence lifetime as a function of temperature for the red, the green and the blue level. And that nicely followed the multiphonal relaxation law, where the multiphonal relaxation, so the vibration relaxation, scales with 1 plus the phonon occupation number n to the power p, the number of phonons that you need. So from those fits for the low concentrators, low doped samples, we exactly understood what is the multiphonal relaxation rate from all of those levels as a function of temperature. Then we increased the concentration of holmium and we determined the cross-relaxation rates. And that was nice fitting done by Freddy Rabau, a very brilliant guy, where we used the shell model, we used the real crystal structure, and for every concentration we determined the distributions of holmium ions around the central ion, and with that for every concentration you can calculate the luminescence decay curve using one parameter, one fitting parameter, C, the interaction parameter for energy transfer, dipole-dipole energy transfer between the two holmium ions, assuming that the energy transfer mechanism is dipole-dipole interaction, which has a R-6 distance dependence. So now we have two parameters for the multiphonal relaxation, we understand for all the three levels, the cross-relaxation, and now we can calculate for any concentration, any temperature, what is the ratio between the green and the red emission. And that nicely follows. So the dots are what we measured, the lines are what we calculate for the 0.5%, the 12%, and 30%. It very nicely follows our model. And then you also can see the shift from red to green for the 12%, and for the red, where the cross-luxation is faster, you have to go to higher temperatures to have that same type of shift. So we really understand the physics of this thermometer. What's also nice is now we can calculate, as a function of temperature, what is the relative sensitivity. And you see that this whole medium energy transfer thermometer has a much wider range where you have a pretty good 1% per Kelvin relative sensitivity. And any Boltzmann thermometer, when you go to high temperatures, when you get more equilibration between the two levels, this relative sensitivity always falls off like this. And of course, where it falls off, that depends on the energy gap. And for a smaller gap, it's focused more here at lower temperature. For a higher energy gap, it's more here. But you always have this very narrow window of temperature where you have a high relative sensitivity. With energy transfer thermometers, you can have a more extended temperature range. So that's nice. Then, understanding temperature accuracy. How accurate or how precise can we determine the temperature? The main factor that we discovered for the precision of the temperature that you can determine is just statistical random noise in your intensity, Poisson noise. And we did some simple simulations. If you have a expected, this is an emission peak, and when you have a peak intensity of 100 counts, then the error in that Poisson statistic tells you is the square root of 100 is 10. So we simulated emission spectra, just assuming that the intensity from the two levels A and B was the same. And then you calculate what is the ratio between the emission from the lower level, emission from the higher level. And from that, with your Boltzmann equation, you determine the temperature. Then because there are statistical variations in the intensity, sometimes in your experiment, you will measure a slightly lower intensity for the blue level, and then you calculate the lower temperature. Sometimes the intensity for the red, the lower level, is a bit lower, then you calculate a higher temperature. So the statistics shows that you have a pretty wide spread in temperatures that you determine from randomly measured emission spectra when you have a low intensity. When you increase the intensity by a factor of 10, go to 1,000 counts in the peak, then the deviation becomes much smaller. So the variation in temperature, the uncertainty in the temperature, is 1 over the relative sensitivity times the variation in the luminescence intensity ratio over the luminescence intensity ratio. So that was theory, simulation, and we also did experiments. Kind of boring. You have a system, you keep it at fixed temperature, about room temperature, and 200 times you just, with a CCD camera, it's actually quite fast. You measure your emission spectrum, determine the intensity of the higher level, intensity from the lower level, from the ratio determine the temperature, and then you see just for the same setup at room temperature, you see that the intensity that, from the intensity variations, you get a variation in the temperature that you calculate. We also made sure, we're careful that we did not have any laser heating, because you can imagine if you have a high laser power, that you get more signal when you get some laser heating, so that the temperature that you calculate is then related to the total number of counts, but there was no correlation at all. We were well below the laser heating limit. And from that we could see that, yes, indeed, the noise, just the random Poisson noise, determines the accuracy in the temperature that you determine. And as a function of temperature, you see that when the relative sensitivity goes down for this Boltzmann thermometer, this error goes up, and the curved line is what we calculate for the temperature accuracy, and the dots is what we measure with those type of 200 times. Just measure spectrum, 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 determine the temperature from the spectrum, and that very nicely follows. So it shows that, one, Boltzmann, Poisson statistics determine, so the signal determines how accurate, how precise you can measure temperature. And the second message there is that signal matters. You can have a very nice high relative sensitivity, but if you have your poorly luminescent thermometer with a low quantum yield, well, then you still get a very bad temperature sensor. So signal really matters. Strong absorption, high efficiency are important to obtain a good accuracy. We also looked at the role of the background. So we measured the spectra by not only having the emission from our temperature sensor, but we also just had a random lamp spectrum that we knew exactly what that spectrum looked like. Then we deducted that. Then you get a corrected spectrum that looks very much the same as the normal spectrum. But now, because you have more background signal, that adds extra noise, and that induces more inaccuracy. So depending on how much your background is, you can again calculate what is the variation in the temperature that you get over the wide temperature range. And then you see there was no background. You get a pretty good accuracy. The best is about 0.1 Kelvin. But when you start to have background signal, then the accuracy very rapidly gets worse to 0.3 or 0.5 Kelvin. So also the message is that those theoretical resolutions that people claim based on solely relative sensitivity, where they claim a millikelvin accuracy, that is not possible. Noise, random noise, determines that for a luminescence thermometer we get never much better than 0.1 Kelvin. But we're not there yet. Temperature accuracy is nice, but shifts happen. And those shifts can be due to all kinds of factors. The background I already mentioned, but also wavelength-dependent light scattering and light absorption are crucial. When you have your material that you develop and you put it in your sample holder in the lab, in the spectrometer, you get very beautiful spectra, everything looks beautiful, but then you put it in a biological system. And then there can be light absorption by the system, can be light scattering. And if that depends on the wavelengths, and one wavelength from the lower emission level to the high level is different, then what you detect at your detector, that ratio is not reflect what your probe emitted. So the temperature that you calculate then from your spectrum is not the actual temperature from the position where the probe is. Then there can be additional signals, overlapping signals, especially the higher laser powers that has been observed. There can be calibration errors, very nice. If you look at the literature for this very famous system, sodium hypofluoride, doped with erbium and terbium, the delta E that people calculate varies from 700 to 800 wave numbers. Same system, that gap should be exactly the same, and yet in the literature, depending, I think, on what temperature range they use to do the fitting, maybe on their equipment, it varies. And it shouldn't vary, it's fixed. And of course, when that varies, you get a calibration error, a systematic error. Related maybe also to the detector and monochromator. Then there can be photonic effects, and I will also give an example of that. And Thomas van Swieten did very nice work, also with Freddy Rabau and me, and he just finished his manuscript. It's going to the committee, and Dani Jacques can approve it or not. And if you're interested, then you can also send me an email, and I can send you the thesis. Of course, a lot of work has also been published. So one interesting thing to distinguish is between accuracy and preciseness. And this is the picture that Thomas thought of. Accuracy means that the temperature that you get from your spectrum is actually the exact temperature that the probe has. And then if you have low signal, then you're not so precise because the variations, the noise level is pretty high, so you're not so precise, but it's all around the accurate temperature, the exact temperature. So there's a shift due to noise, but there's no shift due to systematic errors. And then, of course, if you measure for a long time or you have a very bright sample, then you can have an accurate and precise measurement. However, if there's artifacts, there's additional signals. For example, there's emission from a higher energy level that you integrate with the emission from your lower energy level, but that shouldn't be there. Then you get a wrong temperature. Even if you measure for a very, very long time with a very bright signal, you get a deviation from the exact real temperature, and then it can be rather precise. The width of the ring is small, but there is a systematic error. And yeah, how to correct or avoid those systematic errors. I will give a little bit of information on how we've done it for some systems, but this reduced the accuracy. And of course, noise reduces the preciseness. And also you have to realize then that there's a trade-off between time resolution, spatial resolution, and temperature resolution. For good temperature resolution, you want to have a very high signal, good signal-to-noise ratio, but that may mean that you have to measure longer or measure over a larger area. If you want to have a high spatial resolution of a micrometer, then the number of emitters in that micrometer that you probe is small, so you get less signal. So there's a real trade-off between time resolution, spatial resolution, and temperature resolution. And the parameters that you get from your nice, simple lab experiment, where you just have your sample in your spectrometer, you can measure for ages, beautiful spectra, very nice, low noise spectra. You cannot realize that in a biological system. So we have to realize that. And again, brightness, efficient, high quantum yield, strong absorbing probes are important. So laser power can be a problem, very trivial, and that's often recognized in the field, is that you can get laser heating. When we did that same experiment, measured 200 spectra at a slightly higher laser power, then we did see a correlation between the temperature that you get out and the total number of counts. For the higher count rates, where probably there was some laser heating going on, you got a higher temperature versus this one where we were at reduced laser power. But also, what you can have is at high laser power, and that's especially important in confocal microscopes when you want to have this high spatial resolution, and you crank up your intensity of your excitation source to get enough emission out to get micrometer or 10 micrometer resolution, then you can have higher order upconversion processes. So for the ytterbium-erbium couple, you excite at 1,000 or 980 nanometers, and you transfer to to the erbium ion, second ytterbium, brings it to this 2H11S4S3F couple, you get the two emissions. But at high intensities, there can be a third absorption to an even higher level, and then you get emission from the 2H9S level. And you really see it when you go from 0.3 to 0.6 to 1 kilowatt per square centimeter. You see that when you scale on those at this constant temperature, that is emission from the 2H9S level increases. And now when you integrate this area sinking, this is all for S3 halves emission, then the temperature that you calculate is lower than the actual temperature. So we did some correction for that. We fitted the spectra and we knew how the 2H9S emission looks like, and then you can deduce that. And then this is an experiment I will discuss in more detail later. We looked at a spiral of about 200 micrometers, the temperature distribution to see how homogeneous the temperature distribution on this heating spiral that you use in electron microscopes or synchrotron experiments is. We see that, you see a change. This after correction, you see, first of all, that the temperature gets a bit higher, as you expect. But you still see that the spiral seems to have a different temperature than between the spiral. And that's weird. You don't expect that, because it's just at room temperature. Those are photonic effects. I will explain them later. Fifth pitfall, the wavelength-dependent light absorption and scattering. I just explained that when your medium where you have your temperature probe in doesn't transmit the spectrum at all wavelengths at the same way, because part of the wavelengths are absorbed more than other wavelengths, then you get wrong readings. One way that you could correct for this is to add an additional broadband emitting probe with a very well-known and hopefully temperature-independent or hardly temperature-dependent spectrum. And then you measure not only the intensity from your luminescent probe, to the lower level and the higher level emission, but also the spectrum from this broad probe. And then you correct the intensity ratio that you measure for those two peaks by the local density of state that you calculate from the known emission spectrum and the emission spectrum that you have with this different photonic environment, or this different absorbing environment. So then if you look at the ratio that you measure, you have to correct or multiply with the local density of state of the bulk divided by the background for both spectra, and then you get the same ratio. So in theory that works, and it's actually inspired by this paper where they did that for Raman spectra, where when you want to deduce temperature from Stokes, anti-Stokes ratio of Raman peaks, you have the same problem. If the Stokes and anti-Stokes are absorbed or scattered differently, you get the wrong temperature. And they try to do that with a broadband emitter. You have a dual functionality probe. In theory it works. In practice it's still hard, but we have to work at it. We have to solve that problem to get accurate temperature measurements. So that brings me to applications. So this is just some basics on all the things that can go wrong with luminescence thermometry. Maybe not a very happy message, but we have to think about it. But of course, lots goes well as well. So if you look at mapping temperature profiles, then mapping the temperature profile of L-tide is quite simple. It's hot at the bottom, cold at the top. And with a simple thermometer, you can measure it and then make a nice temperature map. But when we look inside catalyst beds or mapping of the temperature distribution on a microheater of 200 micrometers wide, then you cannot stick your thermometer in. Then you need those nice nanoprobes, those luminescent nanoparticles that you can put inside your catalyst bed, that you can distribute on top of your microheater, and in that way measure the temperature with very high spatial resolution. Challenges here are going to higher temperatures, higher spatial resolution, and higher accuracy. And that holds for microheaters, microfluidics, where it's not easy to measure temperature inside the microfluidic channels, and also at a real place where the catalyst is active, what is the temperature there, may be different than the temperature in the solvent, and in the biomedical field as well. So this is work we have not done much in the biomedical field. We don't have the facilities for that. So this is a nice paper from the Dani Jacques group. So this is the model system. I already mentioned it. Sodium fluoride, doped with erbium and terbium, excite at 980 in deuterium, two-step energy transfer, nice upconversion emission in the green. Good thing is that you have very little background there because the background does not show upconversion. So you do get nice clean spectra. There's little background, which is important. When you go to high temperatures, it's a problem because those nanocrystals are not stable when you heat them to high temperatures. They agglomerate and the stability is reduced. So what we did is to make nice stable particles. We grew a silica shell around it. They get those nice particles. So the core is sodium fluoride, ytterbium, erbium, a nice silica shell. It also makes them water soluble, which is also nice for some applications. And we also did some thermal cycling to look at the reproducibility, and yeah, they're beautiful, reproducible. They're very stable. You can heat them up and down, heat them up and down. That's also important. Nothing changes. So, for probing catalytic reactors, we grew our core, sodium fluoride, ytterbium, erbium, grew a shell around it. You see, there's very nice monodisperse nanoparticles with the core, the optically active core, and a silica shell. Then we put them in the extrudates that we put in the catalytic reactor. And then this is the final setup, where there's an optical fiber here, where we excite through an inner fiber core in the 980 nanometers, and the fibers around it collect the emission, and we can do that at different positions in the catalytic bed. And then this is what you see. At the top you see a fast rise when you do this methanol to olefin reaction, polymerization reaction. The temperature is an exothermic reaction. The temperature rises very quickly in the top, and then it falls off, but it always stays warmer than in the middle and the bottom, because there the temperature goes up slower, and then the catalyst spoils, and the reaction is not as effective anymore in the middle and the bottom. So you can probe at different positions in your catalytic reactor the temperature at very high temperatures. Maybe also good to realize that a lot of this temperature sensing, luminescence temperature sensing, is enabled by new equipment. We now have fiber optics where you can have those fibers with like 7 fibers, where you can use the central fiber to excite your sample and the fibers around it to collect the emission in this way. And you can then couple this one to a laser and this one to your spectrometer. You have nice compact CCD spectrometers. So the miniaturization giving rise to very cheap also the laser diodes, nice compact cheap excitation sources, monochromatic. That has really also made it very easy to use luminescence to detect temperatures. Microfluidics. What is the temperature inside those microchannels? 50, 100 micrometers wide. You cannot stick a thermometer in there. But if you put your nanoprobes in there, you measure the luminescence inside the channels. At any spot of your microfluidic device, you can determine temperature. So we've done that as well. And this is just one where we used 2 spots. One spot that was very close to the platinum thermocouple, and there you see that the temperature that we get from the luminescence spectra is very similar to the set point temperature, but at a spot a bit further on, the temperature, the actual temperature is lower than the set point temperature. So those nanocrystals, by measuring the luminescence at any position in a microfluidic device, you can determine what is the temperature there. Then those microheaters. The Den Solutions is a company that makes those microheaters, and 70 micrometers wide. They used, as I said, in electron microscopes to take images at elevated temperatures or in synchrotrons. They're very small, and the question is how homogeneous is the temperature over this microheater? So we deposited our nanocrystals on the microheater, and then in a confocal microscope did the mapping, and then we saw this strange effect that on the spiral the intensity is higher. So this is just this emission spectrum, one of those spots. And we can go down to a micrometer by a micrometer spots. This emission spectrum that you measure, and then you see that on the metal heater the intensity is higher, but the temperature that you use is smaller. So that has to be an artifact, but what? Well, what it is a photonic effect, the Drexhagen effect, which is quite well known. If you look at emission from an emitter close to a mirror, there's interference between the direct emission and the reflected emission from the mirror. And it depends on the wavelengths if that's constructive or destructive. So the intensity ratio, it's determined by emission from at the two different wavelengths. The two different wavelengths will have constructive or destructive interference at different distances. And that affects the ratio of the intensity. If we correct for that, and we can correct for that, it's not easy, but then you get a nice homogeneous temperature distribution. And you can see that at elevated temperatures, it starts to fall off at the edges, but in the middle, it's nice and flat. So that brings me to my conclusions. I think a very important conclusion, maybe I've talked about all the problems, but the very important conclusion is that luminescence nanosmometry is a really promising method for remote temperature sensing. From a distance, you can measure the temperatures, high spatial resolution. It is not contactless, as some people say, because the probe is in contact with the medium, but it's remote sensing, which makes it very easy. But shifts happen, and there's different shifts, there's random variations, which causes random shifts of the measured temperature or the determined temperature from the real temperature, and that limits the temperature precision to about 0.1 Kelvin. Very important to reduce the noise is that you make very bright probes. That's something that people should consider when they present their wonderful new luminescence thermometer. We have to look at the sensitivity, the brightness, whether or not you have Boltzmann equilibrium, artifacts, systematic errors like laser power heating, photonic effects, background, calibration problems, difference in absorption or scattering. And these can really prevent commercial application. And I think that the field needs to recognize the importance of the reliability and address standardization procedures of the equipment that is used, the performance parameters, how they're defined, how they're measured. That is really important to advance the field. And some efforts have been done. There's a beautiful nanoscale paper. But that's something that we have to realize to make it also commercial applicable. With that, I'd like to acknowledge people from the group: Thomas van Swieten, Romy Geitenbeek, Freddy Rabouw, Mark Soete, De Tjauju, Anne Kaczmarek, Alfred Blader, Beck Wekhuizen in Utrecht for the various experiments that I've discussed. The Nano-TB Tech Consortium with the team of Miroslav Dramikanin, Luis Carlos, Artur Bartkiewicz, Dani Jacques, Bruno Viana. Wonderful European consortium. And then, acknowledgement too, I also like to thank Jorge and the whole team that's organized. It's really a wonderful and professionally organized meeting, both scientifically, but also I'm sure we'll have a lot of fun again, just like 4 years ago. So with that, I'd like to thank you for your attention.
Thank you very much, Andries. Okay, a quick question there. Antonio?
Well, I will use my voice like I usually do in this kind of conference. Professor Meijerink, one thing first, thank you for your wonderful talk. I'm not used to use statistics. I'm more a one-time measuring, one-time publishing, but this for sure brings a lot of rigor to the field of luminescence thermometry that some of us are working for some years. So going to the point, you have insisted in the importance of not relying just in the relative sensitivity to report results in the thermometry, and the importance of brightness. First, a comment for you to confirm that will be irrespective of being in a thermometer that works in the Boltzmann regime or not. Right? Working in semiconductor
the same is true for the energy transfer monitors. You have exactly the same random noise problem as in the Boltzmann thermometer.
Yeah, but I mean, beyond our popular but Laporte-born limited lanthanides, in any sensor it will be relevant to have, talking roughly, an average of 20 points better than a one of 10 points. So that will be extrapolable to any different thermometer, right? Like the importance of reporting, taking into account the brightness.
And so
The brightness of a probe is always important, whether it's a Boltzmann thermometer or energy transfer. The noise of that's determined by the intensity of your signal determines the preciseness with which you can determine temperature. Yeah.
And then my question will be, for you to elaborate, if possible, then the golden trio to report, if we want to standardize and to make more rigorous the field, should be the relative sensitivity, the temperature uncertainty, and for instance, I don't know, I'd like to know your opinion, the signal to noise ratio, eventually. I mean, something that gives the reader, irrespective of the system, irrespective of the lab, irrespective of the conditions, some insight about which is the brightness related to the noise, which is the result.
Yeah. So signal to noise ratio is very much determined by your experimental conditions, and that will vary. If you want to measure very rapidly dynamic processes, or you have a very static setup where you can integrate for a long time, that will affect the signal to noise ratio. So the brightness, so the absorption strength and the quantum yield of your nanoprobes, those are the important parameters that you need to quantify. Yes.
Okay, one more quick question here.
Thank you for the excellent talk. I'm wondering, so oftentimes in these upconversion nanoparticles, there's a shell that can be put around the core. How does that affect the properties of the temperature sensor?
So often we work with core shell nanocrystals. You have your sodium fluoride, doped with erbium terbium, and then you grow up an inert shell around it. That increases the quantum yield, because the surface ions are close to high energy vibrations, surface defects, that quench luminescence. So the quantum yield can go up from 1% or 0.5% for a core particle to 8% for the best core shell nanocrystals. So that improves the quantum yield, the brightness. The temperature sensing properties are not affected at all, because the erbium ion is still exactly the same with those two levels, 4S3S, 2H11S. They don't know at all if there's a shell or not. So you improve your brightness, so that's good for your preciseness, for your signal-to-noise ratio, and the performance of the thermometer is not affected at all.
Okay, thank you very much. So let's thank again Andries.